Hi, pre-calculus students. Today we are going to talk about sequences. We're going to review sequences, which you learned back in Algebra 2. So we're going to start with this math note, and this math note actually comes from the geometry book. So sequences are actually first introduced in CP/M Algebra 1, but you all didn't have CP/M Algebra 1. And so mostly you saw sequences back in Algebra 2. So we're going to kind of just go over the two main types of sequences today, and then we're going to build on that throughout the chapter. So there are two main types of sequences. They're called arithmetic and they're called geometric. So first of all, in this math note, it says a sequence is a function in which the independent variable is a positive integer, usually called the term number, and the dependent value is the term value. The sequence is usually written as a list of numbers. So for example, here's an example of a sequence: 4, 7, 10, 13. There's some sort of pattern going on. All right, so we talk about, we would say something like the first term is 4, the second term is 7, the third term is 10, the fourth term is 13, and so on. And there are a couple of different ways that we can, a little bit of different notation we can use. So one way that you learn how to do this is you would say something like T of 1 equals 4. That means the first term in the sequence is 4. And then we could say T of 2 is 7. That means the second term in the sequence is 7. Okay, the third term is 10. So T of 3 equals 10, and so on. Okay, so a lot of times when we would write a rule for a sequence, we would use T of n notation. So in this sequence, and we could also have a table where n is the term number and T of n is the value of the term. So for the first term, 4, second term, 7, and so on. When you look at this sequence, you might notice that the pattern is that it's increasing by 3 every time, right? And so we want to write a rule for that. Now, in general, we know if we see something increasing by the same amount every time, it's linear. And the amount that you're increasing by is your slope. So the rule for the sequence, we'd have T of n equals, and we know it's 3 times the term number plus, now normally when we write an equation for a line, like y equals mx plus b, we have the slope, which would be 3, and then like the b value, or your starting value. So basically that starting value is like your y-intercept, or in this case, it's like if we could back this table up to term 0, what would it be? So what must have been here? So if I add 3, I get 4, and that would be 1. So 3n plus 1. So here's an example of that right here. T of n equals 3n plus 1. Now, there's another way that we can write that sequence, and it's called, it's like a sub n notation. So right here, instead of saying T of n, sometimes you'll see it as a sub n equals 3n plus 1. It's just a different notation. So when you see that, it just means the same thing, right? We would say like a sub 1 is 4. That means the first term is 4. A sub 2 is 7. A sub 3 is 10. That just means the term number. Just like I said, a different way to write it. Okay, then here it says another way to write the equation of an arithmetic sequence is by using the first term in the equation. So if we wanted to use the first term in the equation, then it would be a sub n equals whatever your slope is times n minus 1 plus a sub 1, where a sub 1 is the first term. So you might be like, well, why would I ever want to do that? And where did that even come from? So if we kind of look back to our table, if we look at this a little bit differently, and if we think of this as repeated addition. So if I have 4 and then I'm going to add 3 to get to my next term. So it's 4 plus 3, and that's where the 7 comes from. And then to get my third term, I'm going to take this 4 plus 3, and then I'm going to add another 3, and that's where the 10 comes from. And then here I'm going to have this, my previous term, and then I'm going to add another 3. Okay, so you see in all of them, you have your first term, that's this right here. And then you see you're repeatedly adding whatever your slope is, that 3. But to get the second term, I'm adding only 1 3. And to get my third term, I'm only adding 2 3s. And to get my fourth term, I'm adding 3 3s. So if I wanted to get my 10th term, I would do 4 plus. I don't want to write out all those 3s, but notice the pattern here. I would have to do 3 times whatever term number I'm on less 1, right? Because if it was term 4, I only had 3. So I would do 10 minus 1. And so that's where this n minus 1 is coming from in the rule. Okay, so if you just want to go directly to a rule without having to backtrack and think, oh, wait, what would the y-intercept be? Okay, and I should have said this before, and I think I did say it a little bit, but in an arithmetic sequence, it's the common difference is constant. So if you're adding or subtracting the same amount every time to get from one term to the next, that's an arithmetic sequence. Okay, so that's what we saw here, an arithmetic sequence. All right, so now let's talk about geometric sequences. And the difference between arithmetic and geometric is in a geometric sequence, it's not that you are adding or subtracting the same amount every time. It's that there's a common ratio or a multiplier. It's that you're multiplying by the same amount each time to get from one term to the next. So for example, in this sequence here, it's times 3 times 3 times 3 times 3. The multiplier is 3. In a geometric sequence here, we're you might look at that and say, oh, I'm dividing by 4 every time. I'm not, right? 32, that's divided by 4. Right, so we're dividing by 4 every time. No, we're not dividing by 4. What's the matter? I'm missing a term. I'm like, why isn't this working? I should have a 16 here. That's why it wasn't working. There's always a mistake in these videos, right? Every time. All right, here, I'm dividing by 2 every time, right? So half of 32 is 16, half of 16 is 8, half of 8 is 4, half of 4 is 2, and so on. So we say the common multiplier is 1/2. And you might be thinking, well, isn't that the same thing as dividing by 2? And it is, but when we write rules, we always want to think about what did you multiply by? So if you're ever noticing that you divided, you just want to rethink of that as multiplying by the reciprocal instead. So dividing by 2 is the same as multiplying by 1/2. Okay, so now when we write a geometric sequence, if there's a multiplier, you should be thinking, oh, wait, that reminds me of exponential equations. And we know from before, if you look here, compare these equations for a continuous exponential function. We know it's of that form, a times b to the x, where b is the growth or the multiplier and a is the starting value. And if you look at these formulas for the sequences, right, this is really the same thing, except for we're using an n instead of an x, and we're thinking t of n. So like for this one here, if I say n is my term number, and I say t of n, or we could write a sub n, is my sequence value. And I notice that every time I am multiplying by 3, so then that means that my multiplier, my b value is 3, so I'd have t of n equals, if I'm multiplying by it's like 3 to the n power, but this was like my first term. It's like I needed to know what term 0 was. So if I back that up, then this would have been a 2. So 2 times 3 to the n. So that is where they are getting this rule here. You could rewrite the same thing and use that a sub n notation instead. This should be a subscript, not a power. A sub n equals 2 times 3 to the n. All right, and then they also talk about you could write a first term form of the equation for a geometric sequence as well, and it would be a little different. It would look like this. So you see the multiplier is still 3, but they started with the first term of 6. And so the way they did that is sort of similar to how we did it with the arithmetic. So I'm just go back to what I had here and the 6 and the 18 and the 54, but thinking about how we got that. So this is just 6. This is like 6 times 3, which is 18. This is take my previous answer and multiply by another 3. Okay, to get the fourth term, it would be 6 times. I would take my previous answer and then another 3. So if I wanted the 10th term, I would know I have to start with my first term 6 times 3 to the, now this is like 6 times 3 to the first, and this is like 6 times 3 to the second. This is like 6 times 3 to the third. Notice the difference between the power, the term number, it's 1 less. So this would be 3 to the 10 minus 1 or 3 to the 9th. And so that's where they're getting this from here. Right, so it's the first term times the multiplier to the n minus 1 power. Okay, so that's just another way to write that formula. And if you look down here, this is actually the math note that we're going to hand out in class. If you look down here, for, in general, your arithmetic sequence. You could think of it this way, right? If you know the slope times n, and then you could easily figure out the y-intercept, you could write it like that. Or here's that first term form, right? The first term plus the difference times n minus 1. And then for a geometric sequence, the first term times your multiplier to the n minus 1, or if you wanted to think about it instead of n minus 1, if you want to use term 0, and then this would just be to the n, you could also think of it that way. All right, so now what we're going to do is we're going to look at some practice. And if you look, and this is from the slides, this is slide 7. This right here actually pulled from my assessment resource page for algebra. This is what we've been doing in CPM algebra. But I have the formulas there, right? M is a sequence generator, B is term 0. You can write it either way. And then here, same thing. Now we also have what we're going to call a recursive form. And a recursive form is where they give you like the first term, they give you something, and then they give you a rule for figuring out the next term. And so we'll see some examples of that as we go through some of the slides. We're not going to go through every single one of these slides, but we'll do kind of hopefully enough so that you get the gist. Okay. So if we go back here, it says write an explicit rule. So an explicit rule means if I want to get the 100th term, I can plug 100 into my rule and bam, I will have that 100th term. Recursive, and we'll see this, means if I want to get the 100th term, I have to crank out the first 99 terms first, which is going to be really tedious. Okay, but then there are some sequences that you just can't write an explicit rule for, so that's why we have them around. Okay, so write an explicit rule for this sequence. All right, so first I want to decide, is this arithmetic or is it geometric? So what's happening from here to here to here is that I'm adding 6. Okay, if I'm adding 6, it's arithmetic. And you could write it either way. This is term 1, right? This is term 1, T of 1 or ace of 1. So I could write, you know, T of n equals 6n. Now my B value though would be that I have to back it up. So what must this have been so that when I add 6, I get to -2, and that would be -8. So minus 8n. So that would be my rule, or I could write ace of n equals 6n minus 8. All right, so let's look at another one. Okay, now write an explicit rule for this one. So first, what's the pattern? To get from here to here, here to here, here to here, you might say, oh, I'm dividing by 3, but remember, we're going to think of it, instead of as dividing by 3, we're going to think of it as multiplying by reciprocal. So my multiplier is times 1/3. It's geometric. I could write it like this, or remember we talked about, we could write it as the first term times b to the n minus 1. It really makes no difference. So if I wanted to think of it this way, if this is term 1, then term 0, because that's what I need here, would be, back it up, right? Times the 81 by 3, this would be 243. So I could write ace of n equals 243 times 1/3 to the n. Or if I wanted to use this, then I don't have to back it up. I could just use my first term of 81 times 1/3 to the n minus 1. Now, what's really important here is that if you have a fraction or something negative, that has to go in parentheses with the n on the outside. You may have noticed that I didn't have to do that in the last one, but here it makes a difference, because if you write it like this, only the 1 is powered. Okay, so you have to have that in parentheses. I'll clear these. Clear. Okay, there it is. All right, write an explicit rule for this one. So we see, oh, what's happening? Times 5 times 5 times 5. If I'm multiplying by 5, it's geometric. I could, again, just go for the first term notation or formula. And sometimes it's faster because I don't have to back it up to figure out what the start was. So 10 times 5 to the n minus 1. So here I don't necessarily need parentheses here. If you have them, it's not wrong. But because it's not a -5, it's not a fraction, I don't have to have it. All right, let's see what else we have here. We did a bunch of these. Let's see here. Something different. An explicit rule. There's a ton of them. Let's go back and do that one though. Okay, now this one is, here's one. This is times what? -1/2. Right? It oscillates. A negative times a negative is a positive, positive times a negative is negative. All right, and then you can see for our rule for this one, I put that -1/2 in parentheses. Just be really mindful of that. All right, now write the first 6 terms of this sequence. So if I want the first term, t of 1, I can just put 1 in here for n and say, oh, that's 7. And if I want t of 2, I could put 2 in here for n, and I could get 12. And for t of 3, I could put 3 in here and get 17. But then you might start saying, oh, look, I just know because it's arithmetic, it's linear, that I add 5 every time. So you could really figure out your first term and then say, oh, I just add 5 every time, and then just go ahead and crank out the terms, right? Because you know, oh, from that, the structure of that, that's in that arithmetic form, and that m is my multiplier, right? So I could get my first term and then I could go from there. So you can definitely do that. All right, this one, find the first 6 terms of this sequence. So again, I can go ahead and say, all right, well, my first term would be 6 times -1/2 to the first. So 6 times -1/2 is -3. And then I could keep, now for term 2, I could plug in 2 and say, okay, well, that's 6 times, that would be 1/4. So that's 3 halves. Right, and I could keep doing it. You can also say, well, every time I'm going to multiply by -1/2. So if I know my first term is -3, and then I multiply that by -1/2, I get 3 halves. Then I multiply that by -1/2, and I get -3/4. And then I multiply that by -1/2, and then I get a positive 3/8. And you could just keep going and going and going and going. Like once you notice that pattern, you can just use that pattern. You don't have to sit here and crank them all out. There we go. All right, now here's another one. Same idea, just using that different notation. So don't freak out when you see that notation. This just means find the nth term. So this would be the first term. So I do -3 times 3 to the 1 minus 1. So that would be -3 times 3 to the 0. 3 to the 0 is 1, so that would just be -3. Okay, if I want the second term, that would be -3 times 3 to the 2 minus 1 power. So -3 times 3 to the first. So that's -9. But you should be saying, oh, that's a base of 3, right? That's my multiplier. Every time I'm just going to multiply by 3. And then you could just keep doing that until you get all your 6 terms. All right, now this one, this is something recursive. This one looks a little bit different. So they gave you what the first term was, and then they give you this rule to get the next term. So this is T1. This right here means to get the next term. So if I want to get term 2, then I would have to put a 1 here, and that would give me 2. So I put a 1 for n here, then I would put a 1 here. So to get term 2, I have to do term 1 minus 5. So I know term 1 is 3, and 3 minus 5 is -2. So that's my term 2, is -2. Now, if I wanted to get term 3, okay, to make this equal 3, then this would have to be a 2. So then I would have to put a 2 here, right? The ends have to be the same. So that's to get me term 3, right? This adds to be 3. That means I have to take term 2 and take away 5. Well, I know term 2 is -2 minus 5 is -7. So this notation, when you see it, this T of n plus 1, really that just means to get your next term, this T of n just ends up meaning you take your previous term and subtract 5. Okay, so whenever you see this, it means the next term, and whenever you see this, it means the previous term. So you don't have to go through writing this every time. So to get your first term, you were given it. To get your second term, this just means take your previous term, 3, take away 5, get -2. To get your next term, your third term, take your previous term, take away 5, get -7. To get your fourth term, take your previous term, take away 5, get -12. right? So this notation, to get the next term, you take the previous term, subtract 5. And really, once you get going, again, oh, I'm just going to subtract 5 every time, just go ahead and go for it, right? You don't need to sit there and plug into the rule. It's more about recognizing what that means and then translating it into your sequence. Okay, now here's the same thing, but with that other notation. Okay, this just still means the first term is 1/3. This means still to get the next term, you're going to do 1/3 times the previous term. Okay, so just knowing that that's what those mean. So your first term is 1/3. To get your next term, you're going to do 1/3 times 1/3, which is 1/9. Get your third term, you're going to do 1/3 times your previous term of 1/9, which is 1/27. To get your next term, you're going to do 1/3 times your previous term, so 1/81, and so on. Okay, so that is called a recursive formula. These are recursive because to get to the next term, you have to have the previous term. So that's what I was talking about. If I want the 100th term out of this sequence, I would have to crank out the first 99. If I have something explicit and I want the 100th term, I can just go ahead and plug. I can't talk. I can just go ahead and plug in 100. All right, let's go back to this one. No, wait, where's my answer? All right, I feel like I'm missing a slide. So let's pretend we don't have, this is the answer right here, but I'll show you how to get there. An arithmetic sequence has term 3 of 52 and a term 10 of 108. Find a rule for T of n and determine T of 100. So here are the answers. Pretend you can't see them. Let's talk about how we can get there. So it says use the above information to write a system. So if you think about how we can write a sequence. So I know term 3 is 52 and I know term 10 is 108. And I want to write a sequence, right? So to find the sequence, if it's arithmetic, I need to write something like m times n plus, this is like my b value, or like that starting term a sub 0. And so what I'm going to do is I'm going to kind of start with this, and I'm going to start with it twice. So I know term 3, that's when n is 3. I know the value of that term is 52. Okay, and then I'm going to do it again. Oops, equals. When it's term 10, so when n is 10, I know the term value is 108. So to write my equation here, I need to know what m and I need to know what b are. So I have 52 equals 3m plus b, and here I have 108 equals 10m plus b. And I want to basically solve the system of these two equations for m and b. So I'm going to come over here and I'm just going to line them up. I'll take this and put the 108 here. And what I'm going to do is I'm going to go ahead and I'm going to subtract. So I'm going to do 108 minus 52. So that's what 56 equals 10m minus 3m is 7m, b minus b is 0. And so then when I divide both sides by 7, I get that m is 8. That's where this is coming from. All right, and then if I want to know b, I'm going to go ahead and plug the 8 in for m into either one of these equations. So 52, and then this would be minus 24 equals b. So b is 28. That's where I got this from. All right, and then if I want the 100th term, then I can just plug 100 in here for n. So 8 times 100 plus 28 is 828. Okay, so this is an example of an explicit formula because I can just plug that 100 in to get to that final answer. Oops, wrong way. And then this one is the same idea, except for that it is geometric. Okay, so here it's saying the 4th term is 12. Here it's saying the 7th term is 324. Find the common ratio, so what's the multiplier, and then write a rule for a sub n. Okay, so I'm going to think of it the same way. So if it's geometric, and I can use the t of n or the a sub n, it doesn't matter, right? It is, in general, we want to know what a sub, it doesn't matter, you could do a sub 0 or a sub 1. I'm going to go a sub 0 just because it's less exponent stuff here, and then times b to the n. If you do the first term, then this is n minus 1. It's just a little bit more work. Okay, so I'm going to use this. I know the fourth term, so I know when n is 4, the a sub 4 is 12. So I'm going to have 12 equals a sub 0 times b to the fourth. And then I'm going to do the same thing over here, but I'm going to have 324 equals a sub 0 times b to the, now in this case, n is 7. And I want to solve the system of these two equations. And I think I'm going to put this 12 equals a sub 0 b to the fourth here. We had to do this a couple other times, like when we were talking about exponentials earlier in the year. And what I'm going to do is I'm going to divide both of these sides. So I have b to the third over here, right? B to the seventh divided by b to the fourth is b to the third. And then I'm going to do 3. If I do a to the 0 divided by a to the 0, that's just 1. And then 324 divided by 12 is what? 20 something, 27? Yes, I want to say 27, but I'm going to double check that really quick. I'm pretty sure it's 27. Yes, 27. And then, so I have b to the third equals 27. That means b equals 3. And then I can come over to this equation or over here and say 12 equals a to the 0 times 3 to the fourth. So 12 equals, that's 81 times a to the 0. And then if I divide both sides by 81, I get a to the 0 equals what? 3 goes into this 4 times, 3 goes into this 27 times. This is a sub 0. Okay, so then my equation would be a sub n equals 4 over 27 times 3 to the n power. And then that would be my equation. All right, so that's just a quick little recap of a lot of the stuff that you have seen with sequences before. And as we go throughout this chapter, we're going to just talk more about sequences. We're going to talk about adding the terms of a sequence, which is called a series.